All right, questions? Nothing? And this has just been quiet. All right. So we're still on cryptography. We've talked about private key. For the private keys we've done so far were shift, affine shift, random permutations, of which a shift and affine shift is a permutation. It's not random. Everybody goes over to the same pattern. Same for both of them. Random permutation is just randomly assign letters to letters and then follow that as your mix. To unmix it, just go backwards. We also talked about a form of a block cipher. We block it out, and so for the block cipher of this particular one, you just take it and you just rearrange that particular block by hand, and then you go through it. Now we're going to talk about a unbreakable cryptography, which is called a one-time pad. And when I mean unbreakable, I literally mean unbreakable. There's absolutely nothing that you could do if you use this correctly to ever possibly break it. A one-time pad is a variant of a shift. And the idea of a shift, in its simplest form, is you have this whole f of p is equal to p plus k mod n. What's n represent? The number of the symbols, right? Typically the book always has all their examples as 26. Your language doesn't have to have 26. If it's Greek, it's 24, right? It depends. And on the other hand, if you want to add more symbols than just simply the letters themselves, space character is a symbol. Period is a symbol. Hard return, carriage return, line feed, those are symbols, right? This is just a big string of symbols of which you could make n, whatever you want, right? So what we do is we just simply uniformly always use the same k. What a one-time pad does is it modifies this, and so you would look at a plain text is if I have a plain text string, which is obviously just going to be plain text 1, plain text 2, plain text 3, plain text 4, plain text 5, etc. So I have a string going on here. Now, a shift says I'm going to take each of these and I'm simply going to do a plus k, and then I'm going to do a plus k, and then I'm going to do a plus k, and then I'm going to do a plus k. And also put the pluses up above. Plus k, right? Every one of these gets the same shift on a shift, right? What a one-time pad does is simply say, you know what? Let's not use one shift. What we're going to do is we are going to take a random string of numbers and create a random shift string, which is 1, 2, 3, 4, 5, etc. And so what happens now is I no longer just simply shift one fixed shift. Every single letter gets its own particular unique shift. And this unique shift is just simply a bunch of random numbers that we do, right? And so what happens? Well, this will become C1, C2, C3, C4, C5, right? Where each of these, the CI are just simply PI plus KI mod n. So that's what we're doing. What is physically happening here? Well, let's put it this way. If I gave you a bunch of random numbers, and then upon those random numbers, just simply took, like, imagine that K1 through K whatever, those are just random numbers. And then for each of those random numbers, moved them, like the first random number, I'm going to move P1. The second random number is P2. The third random number would be add P3 to it, right? If I have a bunch of random numbers and I basically kind of randomly move them a little bit, what is the string CI going to be? A random string. For all intents and purposes, it's just random. For example, if I had the Gettysburg Address, and I would say that I had 26, let's go 27 letters. I'm going to include the space character as a letter. Is it possible for me to have a random string applied to this so that the entire Gettysburg Address all gets shifted to the space character? Sure, I actually could write it down, right? It wouldn't be random, but random means it could occur. So what could happen? I encrypt the Gettysburg Address and I hand a person a piece of paper and it's all blank. That's the encrypted message. If a person intercepts that, could they ever possibly decrypt it? Of course not. It's absolutely impossible. There's nothing that they could ever do. It's all blank. Like, what am I supposed to do? Well, you need to know the private key, which is going to be what? That random string. How do I undo it? What would I do with every one of those characters? Subtract it, and I would get back the Gettysburg Address. Okay, the blank character minus this number puts me back into this letter. And then we would just go through it. And so decryption just simply is, if I want to get to the plain text, we take the CI, but then subtract the KI mod n. And that's a one-time path. Yes?
Would that encryption still contain the number of characters?
Yeah, you'd have to know the number of characters somewhat, right? But on the other hand, you could, if you didn't know the number of characters and everything was just, you didn't know how long it was, just start using it. Eventually you'll get gibberish. Because, I've gone past this thing and I get gibberish. I'll just get, what are the letter numbers for these random strings? So eventually you'll get gibberish. The important part about a one-time pad is, one, it's unbreakable as long as you focus on the first two words, one time. Right? Because what happens is, if you keep reusing it over and over and over again, they figure out what your one-time pad is by simply letting things happen. I mean, that's a valid technique for breaking cryptography, is if you have it broken or partially broken, and you know that, they're going to attack this particular ship and they're going to sink it, what did we do in World War II if we didn't want them to know that we actually broke their code? You let them do it. Right? You wait for events to happen, you let them happen, and then you have information about that message must have been something about this. Now you can start applying cryptanalysis. If they keep reusing the pad, you can discover the pad through reuse, because you start to get knowledge. They had to have said something about a ship. They had to have said something about the day. They had to have, so you start to break it out that way. But if it's used once, never again, there's nothing you can do. There's actually a statute outside of the NSA that has all these things that are just encrypted. And what people are supposed to do is just go to it and all these secret messages, and you're supposed to break it. And the one that has not been broken is the one-time pad. And the thing is, on the statute is a one-time pad. You just don't know how they used it. Your one-time pad is just a way to generate a bunch of random numbers. Well, we don't know how they used that one-time pad to figure out, what the encryption is. So that's still been unbroken, even though the one-time pad it'd be like this. This book that we use is my one-time pad. And what I will do is, for every message, if nobody knows if you know I use this book, but you don't know how I use this book. If my personal choice is, every time I send a message, what I'll do is I'll say, okay, I'm going to send it on this day, and the person's going to receive it on that day. So today is, 10/23? Today's the 23rd? Yeah, so 10/23. So what I would do is I would say, okay, 10 plus 23 is 33, and so I'm going to go to page, say 33. I'm going to go to page 33 in the book, and I'm going to start on the very first thing that I see, and I'm going to use 2 encode a Sudoku puzzle let, right? And so t, the number for t is my first random O space. Those then become my random numbers. And so classic one-time pads are using well-known books, but we all agree upon we're going to use it in a way that we don't know which page we're going to use, or we would do things like, I'm going to use page 33, but I'm going to use the first number t, but then t is also telling you how to pick my next number. If t is number 15, then I'm going to go to the 15th to get to the next, and not only that, it's going to tell me how to jump around to be able to pick random numbers. Create randomness out of the page. So you might intercept my book, but if you don't know how I'm using my book, if you don't know how the one-time pad's being used, you can't break it. So one-time pads they're easy to do, right? It's just a straightforward bunch of shifts. And one of the things that I'll do sometimes, like as an example, it's always fun, you could simply say things like, okay, the plain text and ciphered text are the same. Let's simply do A, B, C, and D. We only have, so the cardinality is simply N for is 4, right? And then I'm going to take this and I'm going to, okay, let's go ahead and encrypt DAD. And I might do something like things like, boy, I really like pi, right? So people like, you could have little secret things like, oh, okay, you notice 2 people hand each other the secret message, you get a copy of the secret message, and on the way away, you hear the guy say, I really like pie. I like to eat pie. It's like, maybe the one-time random string is pi. So let's use it as pi. What would D go to? C. What would A go to? B. Now what would D go to? D. And so this is the plain text, and this is the ciphertext. And so that's the message that you would send. How would you decrypt it? You would, instead of adding 314, you would subtract 314. So this way we add, to go backwards, we would subtract. Which is the same thing as like if this is in a loop, move right, move left. Move right 3 on a loop, move left 3 in a loop, and it goes C would go back to D, B would go back to A, D would go back to D. Pretty straightforward? So one of the things I tend to do sometimes is like I'll give you a string that makes everything go to the letter A, like A. So that's your entire encrypted message, just a bunch of A's. But good luck breaking that with analysis. Obviously you can't. All right. So one-time paths are the last of our private keys that we were going to talk about. We need to be able to do shift, we need to be able to do affine shift, you need to be able to random permutations, you need to be able to do a block rearrangement cipher, and one-time paths, all of which are rather easy to do. And they're useful. For those that are in programming, you should be able to write these in a reasonable amount of time in basically any programming language. It's not that hard. All right, public keys. We'll talk about one public key, all right? But the concept behind a public key is the following. If I would have as I actually do have a private key. Okay, we have a private key, and let's say that we call it, I don't know. For us, we're going to use 2 things, and let's say that it's the set of PQ. And I need to keep these secret and never tell anyone. The concept behind this is to somehow take PQ, have some sort of mix function that would generate a new single number. And a lot of times for us, we're going to eventually call this like n. And so if this was a product, you could imagine that, for example, an example of something like this is n is actually P times Q, right? P and Q are the random skeleton structure of N. Or sorry, the prime skeleton structure of N. So all numbers are either prime or a product of primes. So I could imagine that N, as an example, then this is what I make public. And I don't have a choice. I have to make it public. Public key cryptography is under the assumption that you have no choice. Everything is heard on all of your communications, and all of the bad guys have all of your communications. You just know that. So what I've done is I've given them the private key. But I gave them the private key in some sort of mixed thing. The strength of this crypto, what has to happen here is when I talk about strength in terms of a term is about this mix function. When I say this public key is this strong, what I'm really talking about is this mixing function. This mixing function is invertible. It can go backwards. And everybody knows what you did. All right? So when I say how strong is this public key cryptography, it really gets down to how strong is your mix function. Is your mix function known, computationally difficult to unmix? So that's what we talk about in terms of strength. It all gets down to the fact that I gave them my private key, but it's been mixed up. And it's mixed up in a known way. Unmixing has mathematical proof around it to say this is going to take them this long. They can have 100 billion computers, and it's going to take them 15 quadrillion years. That's strong, right? That's what we would say. If your study of the mixing function is correct. So public key cryptography is really about the study of these mixing functions. Once we have that, the encryption of a plain text uses N, right? So what we have is functions of plain text, and N is involved, and we spit out C's. And decryption of C uses the private key in some sort of form. And so F of the plain text, C, F inverse of a cipher, but it needs P and Q, will spit back out the plain text. Now again, there's usually some mathematics involved in how we use the private key, but encryption is going to use this mixed up thing, and that'll always give you nice ciphers. To get the cipher back into the plain text, I really need to know what the private key was. If you have the private key, I'm able to finally unlock this and get back to plain text. Now, can you see that if I am the server, right, and I'm communicating with you and I'm asking you to send me information, what happens? The first thing I do is I hand you, here's N. And everybody knows what N is, right? Then you over here take your nice little plain text message, encrypt it using N, hand me the cipher, but the bad guy gets the cipher too, right? They get C, and they have N. But I'm going here and I'm saying, by the way, to easily decrypt it, you have to have the private key. I'm the only one who has it. So I decrypt it, but on the other hand, does the bad guy have the private key too? Sure, mixed up. So he has two tasks. Unmix it, and once they unmix it, they can start decrypting, just as if they were me. So again, the whole strength of this basis is all about how good's mixing. Now,
does the server know the unmixed version of the private key?
Yeah, it does. But what it does is to use it, there's some pre-analysis. And so what we'll do is we'll talk about one in particular. I usually call it Cox cryptography. Everybody else calls it RSA. We'll talk about why in a bit. But that is what normally happens here in actual applications of analysis of public key cryptography. It's the study of mixing functions. you have a private key, which is something, right? It doesn't, we'll talk about our example, which is RSA, uses product as the mixing. But there are other things. There's hyperbolic functions. There's other things that we could possibly do. Decryption usually is these two techniques of encryption and decryption are usually analysis of mathematical functions. And so it really says uses. What do you mean by use? How are you using this mix thing? Well, there's some things that have to happen to be able to use it. What do you mean by using the private key? There's some things that mathematically have to happen to be able to use it. And so a lot of times there's some pre-work that we do to make it a straightforward function. Stuff comes in and boom, it spits it right back out. We have pre-analysis.
That's the secret that the server knows. Is the back
Right. In the end, P and Q for RSA cryptography, Cox cryptography, those two primes are what must be kept secret with some extra information. And that extra information is the things that are necessary for the entire technique to work. It's all about what's going on. All right. So let's give it an example of this, which would be Cox cryptography. RSA is actually reversed. Shamir, I always get that wrong. Shamir and Edelman. The issue is RSA is what we basically know because they publicly publish their work. For Cox, he didn't. He was an employee of a spy agency. So he had this technique before we had it in public, right? And they were actually using this before the rest of it. One of the things that does happen, especially within crypto work and that level, high level of mathematicians that they know that are going to be good about this, a lot of times they hit graduate school, they show promise, and then they disappear. Not because they get disappeared, but because they get hired. And they go in and say, oh, you're doing cutting edge work. You're going to come work for us. There's a lot of recent papers out that with that whole Snowden, when he released all that secret information type of stuff, they started realizing that some of the stuff he said was they're able to, at least they're in application of what they say they're doing, they're able to sniff on encrypted streams at a higher percentage than they should, which led current mathematicians to ask, what would have had to have happened for them to be able to do that? So they started analyzing it, and then they realized that, oh, the initial handshake has a weakness. That if you do pre-analysis to create this, if you have a massive amount of computers, you can do some pre-analysis on your own against the actual mathematics itself, and then you can narrow and get, it's no longer truly random, it's now in a block. And 25% of the time, they fall within something your analysis worked in, so they're going to be able to decrypt the stream. And so they have things like, oh, okay, so I guess what we thought was safe with our pre-handshake is not. And so why did they, if you look at this, well, obviously mathematicians knew about it and they were actually doing it, but they just, they got hired in and they started doing the work. And so it's one of the things that we always have to worry about is this is a race, right? All right. For this cryptography, it's based upon modular arithmetic. And what it does is for encryption, the function of a plain text is just simply takes a plain text, raises it to an integer power, and takes mod n. And for decryption, we take the cipher, and we raise it to a power, and we do mod n. Can you see why we needed to know exponential modulation as an algorithm? Because if you tried to hard code certain things in the past, if we would take, for example, if I would take 2 and I would want to spit out C, I would take 2 to a power mod n, right? And if we would do things like normal floating point stuff, calculator, right? If I would take 2 to the power of 2003, right? It would say infinity, right? What? Floating point, again, what's floating point? Computers have to approximate numbers. This is a very large int. What this is telling me is when a computer represents floats or even ints, computers themselves have a problem of it's, packed around, here's a 0, right? There's my 0. I'm going to have a largest value and a lowest value. What happens to numbers outside that range? They don't exist to me. And normally you just simply say you call them infinity. Well, what if I absolutely must have 2 to the 2003rd power? There's two approaches to it. You can get larger numbers possible by switching, instead of going into floats and representing numbers, you could say that the number 2 in the power of 2003 is actually a string manipulation. If it's a string manipulation, I can represent strings until I run out of memory. Right? So you could say 2 to the 2003 to say 2003, because since that was at 1, right? What's the modulus of 3 to the 200399? It's just simply 27. Right? Well, there's programs like Maxima, which are just simply the beginning of AI languages like Lisp, and it's using actual string manipulation. That's why it can do symbolic mathematics like integration and differentiation, and it can do it. And it actually does it pretty quickly, except it gets a little long. Here we go. All right, there it is. 27 way down to the other end. Right? And that's as you can see, here's a little bar there at the bottom that's sliding over. See it moving? I'm only halfway through. Come on, keep missing all that drag. Get back to the beginning. There we go. And so some of these representations, like some of the programs for Maxima, will do things like give you the first 10 and then put a little parenthesis, 1,000 more digits, and then it gives you the end. So it's like, I can't fit it. So it just simply jams it all together. It'd be nice if they would have actually did a hard return, because it's nice to see the big giant block that way. But this is the difference. This program just makes it horizontal, which is kind of interesting. So we could go to that. But does this still have weaknesses? Sure, I run out of memory, right, as we're doing it. And so you have to have algorithms to take mods of very large numbers of something, right, because that's what we're going to do. We're going to encrypt a stream, and I want it to go quickly. And so that's where that technique that we learned, you write a program to actually do it for you. It's called the power mod technique. All right. Given that we can actually do this, what's necessary, now that once you figure out how to do this with the computer correctly and get the right answer, these are invertible functions. There's certain things that have to happen. One, you have your private key is PQ to large primes. Why do I mean by large primes? The largeness is the necessity of the mixing problem, right? The strength of a technique is how strong is this to unmix. Because what we're going to do is the second thing, we're going to generate two numbers. N is going to be P times Q. M is going to be P minus 1 times Q minus 1. Well, P and Q are primes. P minus 1 is the even number before that first prime, and Q minus 1 is the even number before that first prime. M is being generated for the server to do the decryption, right? That's why we're making M. Eventually, I know I'm going to decrypt, but I'm making M to help me do that. N is going to be part of the public key that we're going to hand out for encryption. The third thing we have to do is pick E such that the GCD of E and M is 1. So M is necessary not only for eventually to do the work for decryption. The encryption decryption is going to be based upon an int. So I need to find the GCD of E and M is 1. What does this actually tell you? That E has a inverse. E has an inverse under modulo M, which would make sense because the only way I can get rid of something that has been raised to the E power is to raise it to a power so that the power becomes a 1. so I need an inverse, right? I need E times something that spits out a 1, and that's what I want. All right. Once we have that, the next thing we do is we find D, which is actually E's inverse, modulo M. Since they're relatively prime, it has an inverse. Okay, fine. Find the inverse. And then from here on out, we actually do our work. The encryption key is you give them E and N. You hand the person E and N, and that's how they're going to encrypt their message. This is note. This is public. The decryption key is D and N. Note. Keep this private. Right? You don't want other people to know how to decrypt it. But how is D found? D was found by inverse mod M, but how do you know mod M? You have to know P and Q. The only way to figure out M is you figure out P and Q, because I need the numbers in front of P and Q to make the M. The mathematics behind why this exists is because P to the E, and if I raise, which is what C is going to be, if I raise that to the D power, E times D is 1 mod M, which means it's equal to 1 plus some multiple of M. But when I take modulo N, which is the number just off of these two, the M is made by what's the even number in front and the even number in front. What happens is that just simply gets knocked out by, if you look at sections we skipped, it's based upon the Chinese remainder theorem. Right? And so basically the M doesn't matter. You take mod N of that power, it goes away, we're just left with the number 1. So it ends up being that you just simply raise it to the E power, you raise it to the D power, those knock each other out, we're back to P. Which is the whole point. Now, is everybody okay, at least with this statement, of how you would begin this process, if you can see this, what you would do? You would create 2 large primes, keep them secret. From those 2 large primes, you would multiply them and get an N, multiply their ones and numbers in front of them to get to an M, pick some power E. All right, normally what you do to pick your E, I don't care what you pick, right? What they normally do is pick a reasonably small prime that does not divide M, because M is a large even number, right? It's actually a divisible by 4, and you want to make sure that E doesn't divide it. And once that's true, like pick E. Well, is this a divisible by 11? Okay, don't pick 11. What about 13? No. All right, pick 13. You know, pick E reasonably small. Once you've done that, you find its inverse. You know how to do that, right? That's whole Euclid and throw it in backwards to find its inverse. And then once you have those 2 things, it's just simply, can you apply these 2 functions? Again, there is still a private concept, but now there is also a public concept. And the only thing that makes this quote-unquote strong, amazingly, is that factoring is hard. But factoring is only difficult when you make the primes large enough. Right? If they're small, it's not that hard to do. So how do you do this? All right. Normally what happens is we all agree upon a particular feature, and obviously we say we pick PQ, and so say example, I'm going to pick P is 11 and Q is 13. Those are not large primes. All right, 2. What's N? What's that, 130 plus 13, which is right? You know, it's 13 times 10 and 13 times 1. So 103. What would be M? 120. All right, so these are necessary for actually doing the encryption and decryption. M is this part that's just doing the back-end math. All right, the third thing that we're going to then look for is to pick our encryption power E. All right, can you think of a prime that doesn't divide 120? Does 2 divide it? Does 3 divide it? Does 5 divide it? Does 7? Does 7 go into 12? No, so, but how many times does it go into it? 1. What's 12 minus 7? 5. Does 7 go into 50? No, so it doesn't go into it evenly, right? And so I'm going to go ahead and pick E equal to 7 because the GCD of 7 and 120 is 1. They're relatively prime to each other. 7 doesn't divide it. That's the easiest way to do this. You can pick any number that does not divide 120. Normally, just pick a prime. Life is easy. All right, now comes the fun part. D is 7's inverse mod 120. How do we find that? All right. 120 is how many 7s plus what remainder?
17 plus 1.
That's 70 plus 49, right? Which is 119, is that right? Yeah. So 1. So, well, I guess this is actually really easy. There's the GCD. 1 is equal to 1/120, right, minus or plus a negative 17 times 7. Is everybody okay with that? The number in front of 120 is 120's inverse mod 7. The number in front of 7 is 7's inverse mod 120. And so this number, what is 7's inverse? Negative 17. Now, do negative exponents even make sense? The answer is no. Right? Because what would that even mean? No, we have to have positive exponents. Okay, what is this congruent to? What is this the same as under 120? 103? So I'm going to we're going to let D equal 103. Are there a lot of D's? Yes. There's 103, there's negative 17, there would be 223. That would also be D, right? So there's a lot of, everybody could get their own D. I suppose in grades you don't want to do that, but here we go. And so now comes the question of use. Now we would actually do this, and so f of a plain text, we would take p, we would raise it to the 7 power, and we would take mod, what was in 143? That's how we encrypt. And to decrypt a cipher, we would take the c and raise it to the 103rd power, and take modulo 143. Okay. What is the greatest number of symbols that this object can encode? Under mod 143, right, it's always going to spit out how many possible numbers? From 0 to 142, which is how many remainders? Because modulus spits out remainders, right? There are only 143 numbers that this thing can possibly work with, which would tell you what about your symbol string? What's the most number of symbols I can work with? 143. Well, what if I'm trying to encode 1,000 symbols? This makes no sense. It wouldn't work. What should I have done? Picked a bigger P and bigger Q, and I get more symbols to work with. Right? So the limitation of this is you look at the n limits how you use this. Then what we do is say, okay, well then how, and we have to come to agreement, how do we do, say, for example, I want to encode Mark. The way the book does this is, for their example, is say, we're going to block this out and pick block sizes of particular components. And so they would go through it and say, if I do English, and I would use all same case, like little m, little a, little r, little k, right? What the book did, if you look at its example so that you don't get confused, they do little m, little a, then they do little r, little k. M is the what letter? Okay, I need to write these things out, darn it. Need to have a nice big thing. 15, 14, 13? Is M 13? Or 12? A would be 0. A is 0. B, C, D, E, F, G, H, I, J, K, L, M. 12. So that would be 1, 2, 0, 0. I need 2 symbols, right? Because 2, 6 would require 2 symbols. R, M was 12. Is that right? We start off at 0. A is nothing. Okay. Then M, N, O, P, Q, R, we're at 17. Back to K, darn it. A, B, C, D, E, F, G, H, I, J, K, 10. 10. What the book does is it simply looks at this, and since they picked, if you pick large enough PQs, you'd notice that, oh wait, I could block like this, because the worst I could have would be, say, 25, 25, right? Which would be ZZ. So if I did a ZZ, I would have 25, 25. That's the biggest I could have. That means my P times Q needs to be bigger than this. Does that make sense? And so what you do is you simply go to blocks and you pick the block size that is largest for us to work with. Since I picked 143, what am I stuck with? Can I do 2 letters at a time? Everybody shake your head. No, I can't. So I would have to, for this one, this is too big. Obviously 143 doesn't work. And so for this problem, for this, I would rather do M, A, R, K as all separate. I would encode separately from each of these. I would say that I have 12. Where does 0, 0 go? Where does 17 go? Where does 10 go? I would take each of these one at a time. On the other hand, I could, scale this up a bit. 143 actually would allow me to do the entire keyboard. So instead of having just 26 symbols, I could go ahead and do, say, all 52 symbols plus punctuation and everything else. That's less than 143. So if I would do uppercase, it starts at capital A is 0, 0, capital B is 0, 1, and then little a would be then 2, 6, little b would be 2, 7, and I could go and go and go and go, and it'd still be one at a time, but I would be able to do a lot more symbols. And then all we do is say, okay, so this is what I would use because this is larger than 143, so this one, we couldn't use the book technique, but I could use this one. And so what we would do to encode is say, cipher 1 would be 12 to the 7th power modulo 143. Cipher 2 would be 0, 0 to the 7th power modulo 143. I already know that answer, 0, 0. Cipher 3 would be 17 to the 7th power modulo 143, and then cipher 4 would be 10 to the 7th power modulo 143, and we would get that. And then to decrypt, we would take whatever those were and raise them to the 103rd power modulo 143, and it would put them back. Everybody okay with that? Is this still, in an extreme case, is this still sensitive to cryptanalysis? Does 12 always get mapped to the same pair? So if I went down then and did this the hard way, I could simply say these pairs of ints, right, always get mapped to the same pair, right? This 12 gets mapped to this number, 0, 0 gets mapped to 0, 0. You could possibly, and since there's only 143, But that's 143 factorial ways that this thing could have worked. And that's impossible for us to do, but you could, maybe, if you knew a little bit of information, you could basically try and brute force it. So there is some flaws, especially with the low primes, but low primes are easy to factor anyway, so who cares? Is everybody okay with that? On how you encrypt and decrypt? And for your homework type stuff, obviously you're going to be doing lots of that. My recommendation is install Maxima. Because it's like, okay, what's 12 to the 7th power modulo 143? Okay. The nice thing about Maxima is I can go here and say, all right, I'm going to take the modulus of 12 to the power of 7 and comma, what was it? 143, close, enter, 12. Interesting. What was the other one? Was it a 10? There was a 10 in there, wasn't there?
Yeah.
Uh-oh. I think I picked this way too small. If you pick poorly, it doesn't mix. If you pick too small, one of the things you have to do is pick some really large stuff. So, was there a 7 in there? What was the other one? 17. I bet it'll be terrible if this goes to 17. And I think it's like, probably is. Nope. Hey, something different. 0 goes to 0. At least that one went to 30. And so Maxima's nice on that. So what was 12? Yeah, it was 12. 17 was 30, and that was 10, right? And that was 0, 0. And then to decrypt, you would say that plain text 1 is 12 to the what? 103 modulo 143, and then plain text 2 is 0, 0 to the 103 mod 143, and then plain text 3 is 30 to the 103 modulo 143. Plain text 4 is equal to 10 to the 103 modulo 143. Let's check that one. 30 to the 103rd power. So what would be 30 to the decryption power that you keep secret from everybody. Don't tell anybody the number 103. And we're back to 17. Everybody okay with that? So on the server side, they still keep P and Q, but those aren't useful. D is useful. So you do all that work for D and M and everything else, and you keep those secret, but you use D to actually do it. For the heartbleed technique, the problem was the server obviously has to load those into memory. And it loads those up into memory and uses them. Now, you're talking to a server that's going to be doing the decryption, right? And it loaded up into memory. The heartbleed technique is, I'm asking for pieces of memory that I'm not allowed to supposedly be asked to. But if your decryption server, right, that you're talking to, allows you to read outside the memory that you were supposed to, like, oh, please read this memory address, and the way you do that is you give it too much, you overflow a certain piece, and it goes and reads way out here. Well, if they make it so that you could just basically index and get as much memory, there'll be spots where it's like, you as decryption application such and such can't touch that piece of memory because it's actually being used by this program. Okay, fine, move to the next. Eventually you'll get all of the memory that that program's actually using, and in that block is the decryption key. And then what have you done? You took it right out of the system, because it has to load it into memory. And so that was the problem with the heartbleed, which is why nobody honestly shouldn't program necessarily in C, or you better be darn good at it, right? To realize that it should be memory safe. You either, if you're going to use C, C++, etc., you humanly must be memory safe. Every time know exactly how it's touching memory. Or switch to a language that's memory safe. It's like, oh, you asked for this. I'm sorry, that variable that you asked for is bigger, go away. It throws it out. It's like, that makes no sense. You know, you're asking for, I have a 16-bit number, you're asking for a 32-bit number. I'm not going to go to memory and give you 32-bit of stuff, right? Which is what it did. But C would happily do that. So either you are memory safe or use a language. But nobody's memory safe, and they use C. Hence, we'll have this problem forever. Is everybody okay with that? So that's crypto. Doesn't it feel great that your entire security is based on factoring's hard? I don't like arithmetic, right? Modern techniques are using in terms of the whole mixing function. Modern techniques for different things, and can we essentially leave RSA, public key cryptography? Most research here is doing that. What are things that we can do that make this, you know, what if they have a quantum computer? I better pick a mixing function that even quantum computation can't do, you know, or efficiently. Factoring, quantum, appropriately set up, can do, but it can't do all factoring. Quantum computers have a subset of all factoring that they can do, so you'd have to stay away from that. So you could still somewhat use factoring, but it would limit your abilities. All right, attendance. Since it's a weekend, you got nothing else to do. Nothing else now. Page 316, which is into the next section. It's just an example. So read ahead, example number 1. And so this is induction. So the next thing we're going to move on to induction, so we actually improve the fundamental theorem of arithmetic. And this would be triangular numbers. The sum from 1 to n is still n times n plus 1 over 2, but you prove it in the induction. All right, that's it.